Buenos dias or good morning. This talk is about a fiber reinforced composite. The fiber is a cylinder with several faces. The cylinder is periodically distributed and the properties are related to transport. I will show three examples of different kind which will reveal some stimulating results. I hope you find them as well as I do. This is the outline of the talk. As far as the geometry is concerned, it is necessary to spend some time describing it. The problem is formulated in general form using flux and potential. Two characteristic lengths are introduced so that a small parameter is found, which leads to an asymptotic method of solution. Finally, a closed form formulas is obtained for the transport properties, which are easy to compute. Three examples are considered, each one from elasticity, conductivity, and fluid. General conclusions are given at the end. This slide shows the geometry. On the left, you can see a cross-section of the composite showing the cylinders in a horizontal position. On the right-hand side, you can see an enlargement of the unit cell, which in this case it is a parallelogram of angle theta. The matrix material occupies the external part and it's denoted by 1. The other materials will follow the numeration up to the number of faces. Each of the rings is occupied by different materials. Here we have the formulation of the problem. F is the flux, phi is the potential, so divergence of F equals 0, where F is proportional to the gradient of the potential. The proportionality constants are transport properties, in this case a tensor 2 by 2, which belongs to the crystal symmetry 6mm. Each property occupies a certain volume fraction, Vi, and the total sum equals 1. Now we discuss the method of solution. We have three columns in this slide. The first one formulates the problem as a Dirichlet one, with continuity of flux and potential across the interfaces of the materials. The rapid variation shown on the coefficients in equation motivates the use of the double scale homogenization method, and the answers as formulated give us a first term which depends only on the first variable. This is the average value of the potential. It turns out that on the third column, the potential satisfies a differential equation of the same type as the original one, but in this case, the coefficients are constant. The coefficients are given here in terms of the average properties of the cell. It involves the properties inside the cell and a function n, which needs to be solved which arises during the solution of the problem here at order epsilon. The n functions satisfy potential problems. The problems are solved using Kolosov-Muskelis-Vili potential theory, and the final solution is given in terms of the residue of Weierstrassian functions. Here, the results of the elasticity problem for 4 phases. We deal now with shear moduli, which are normalized relative to the matrix. Here at the bottom are defined the effective properties P, Q, R, and plotted in this semi-logarithmic plot on the vertical axis. Horizontally, we have P3 and the rest of the other quantities fixed. So you can notice at the lower end of the plot that there is only one property because this is 0 and here we have the collapse of 2 curves. So the material here is isotropic. If we go to the other plot, you can observe that at the lower end of P3, there are 3 curves. So the material here is anisotropic. The difference with the previous one is that P3 here is much softer than in the first case. So this is an attractive property which produces either isotropic or anisotropic material. In this example of conductivity, in fact, complex conductivity, we are considering a 3-phase material with 3 angles of the parallelogram. The model can be applied to muscle cells as Bisegna and Caselli did in 2008, but they did it in a 2-phase material with an impedance condition depending on frequency and conductivity. They plotted the results against this normalized frequency, so we did the same to compare. So we plotted here the real parts of the 2 properties, and we can see that for hexagonal arrays, Bisegna and Caselli, the red dot, and ours, the black dot, coincide in the plot. In fact, you can see only the black dot. For other angles, say 45 degrees, the green dot, you can see it spreads quite a bit. So I'm not going to discuss, there are 3 other plots which can be seen separate from this representation and at leisure replaying the video. These 2 other plots are also related to the conductivity, to the muscle cell application. I'm not going to comment any further, except to say that you may see this video again on repetition and see the details of the plot. As the last example, we have a fluid with complex mass density. This case, as the previous one, has 3 phases. But now let me explain what is the situation here. We have that the mass density of the matrix and the core are the same. The real part of the interface is slightly different from the other two, not the imaginary part. And we have here two limiting curves, the continuous and the dash. The continuous curve corresponds to only two faces. That is to say, where the third volume, the core volume, is zero. The dash curve corresponds to the case where V2 and V3 is equal to 0.8. So the maximum is attained when the filling fraction V2 equals V3, 0.4. And in this case, it attains an inertial enhancement in both cases, because the real part of both mass densities of one material and the other is less than the total effective mass. So there are situations where you have this, and it happens when we change slightly the values of the masses, and it occurs the same phenomenon. So we come now to the section of conclusions. Some general ones about the induced symmetries. We have three, which are tetragonal, hexagonal, and monoclinic. As far as the shear moduli example, in the case of four faces, it's possible to get effective behavior on the isotropic or anisotropic end when you change for an interface soft for hard. The conductivity problem as applied to a biological tissue like muscle cells, the impedance model of two faces can be also attained for the case of three faces with a very thin interface, which is the case of Hashin's approximation. In the last case, where we have mass density, we show that it's possible to get enhancement of the mass density via close values of the two materials and varying volume fractions of the third one. Okay, so that's. And in this last slide, I would like to thank you all for all your attention. And if you have any question that has to come after this talk, well, please, there is my email address there, and I'll be happy to answer. Thank you.